Welcome, participants. We'll be starting the lecture a few minutes after the hour. Hi, everyone. It's just 4 o'clock. We're going to give folks another minute or so to connect in case folks are just coming on, and then we'll get started real soon.
Feels very nice.
Good afternoon. I am Ed Scheinerman, Vice Dean for Faculty here at the Whiting School of Engineering, and welcome to the 2020 Billig-Croft Lecture. I'm excited to see so many participants here with us virtually. Before I introduce today's speaker, I want to thank Gordon Croft for establishing this annual lecture in honor of his good friend, the late Dr. Frederick Billig. Gordon, thank you. We are so fortunate to have you as a supporter, and I hope that you'll be able to join us on campus soon. Thank you to all the members of the Croft family joining us here today. Gordon graduated from Johns Hopkins in 1956 with a bachelor's degree in industrial engineering and has built a remarkable career in finance, including the establishment of the highly respected Croft Leominster Investment Management Company here in Baltimore, which he managed with his sons, Kent and Russell. Gordon has a true appreciation for the overall importance of engineering in our society. He thinks deeply about things that are important to our nation and is passionate about being a catalyst for change. He cares about the work being done here and stays involved with our programming and people on a regular basis. Gordon has been a most loyal supporter of the Whiting School in many ways, in addition to creating this lecture. He has provided scholarships for students from his home area of Port Tobacco in Charles County and established graduate fellowships and 3 faculty scholars. He has also provided generous, flexible support to the school to invest in interdisciplinary programs. In 2013, the university was thrilled to name Croft Hall in honor of Gordon's many years of commitment and generosity. Thank you, Gordon, for your foresight in establishing this lecture and for your overall dedication to the Whiting School. Gordon is always thinking about the most meaningful way to give back to the school, and I know this lecture in honor of his friend and mentor, Frederick Billig, has a special place in his heart. Frederick Billig received his undergraduate degree from Johns Hopkins in mechanical engineering in 1955. After Hopkins, he began his stellar career at the Applied Physics Laboratory. Sharing the accomplishments of Dr. Billig would take all of our time, and I hesitate to even try to summarize the depth and breadth of his professional achievements. Needless to say, he was a true pioneer and a giant in his field. During his remarkable career at the Applied Physics Lab, Dr. Billig focused his research in the area of high-speed, air-breathing propulsion for advanced flight vehicles, including pioneering work for the Air Force in external burning and supersonic combustion. In 1996, he retired as associate head and chief scientist of the aerodynamics department at APL. He also had a remarkable generosity of spirit and mentored many. In the spirit of generosity that Frederick Billig embodied, Gordon Croft established this lecture to bring inspirational people to our campus with the hopes of motivating our students, faculty, alumni, and all members of the Hopkins community. We are pleased to have Frederick Billig's daughter, Linda Baumler, and her family join us today. And now I would like to introduce our 2020 Billig-Croft lecturer, Dr. Tom Foust. Dr. Foust graduated from Johns Hopkins University with a master's degree in mechanical engineering. He also holds a bachelor's degree in mechanical engineering from Pennsylvania State University and a PhD in mechanical engineering from the University of Idaho. Today, he is the director of the National Renewable Energy Laboratory's National Bioenergy Center, NBC, a world-leading organization of approximately 250 engineering and scientific staff performing cutting-edge work to develop cost-effective, environmentally sustainable technology for producing transportation fuels and products from renewable and waste carbon. In addition to his role at NBC, he is also a professor of mechanical engineering at the Colorado State University, a position he has held since 2017. He is an expert in the field of clean energy area with a specialty in sustainable and low carbon energy technologies. His area of expertise in bioenergy include feedstock production, biomass conversion technologies to fuels, and products and advantages uses of biofuels and bioproducts. He has also worked extensively in environmental and societal sustainability issues associated with clean energy. He has over 100 publications in the sustainable energy field, covering numerous aspects of R&D, techno-economic analysis, and environmental sustainability. I am so pleased to have Tom with us today and invite you please to welcome him as today's lecturer. Tom.
Thank you kindly. It's a great honor to be this year's Billig-Croft, named after the distinguished accomplishments that they both, and I'm very honored to be this year's Billig-Croft expert. I'm very excited to be talking to you about an area that I'm passionate about, sustainable energy, and hopefully I can show you why I'm passionate about and why I think this is a good opportunity going forward. So thank you again, and I really look forward to the lecture and questions at the end. So with that said, let me share my presentation. Okay, here it is. And hopefully you're seeing the cover slide, Sustainable Energy, a Vision for the Future. So like I said, it's a great honor to address this group. I think this is really, as I go through this presentation, hopefully I can compel upon the audience really the opportunity space in RIE due to advancements in sustainable energy over the last 10 years. We really have a nice opportunity space in this country as well as the world to move society to a more sustainable, lower carbon future. And that's really what I'm going to talk about. Let me just give you a brief background. National Renewable Energy Laboratory. We're located in Golden, Colorado, suburb of Denver, right in the foothills. As you can see, this is a picture of our campus. We have about 2,200 employees. Our mission is really what our name implies, National Renewable Energy. We were originally founded by President Carter in 1978, upgraded to a national lab status by first President Bush in 1991. And this is really our core values: safe, supportive work environment, leadership for societal impact, integrity, creativity, excellent, and very importantly, a healthy work-life balance. We really strive for that, feel that that's really in the best interest of our staff and society as a whole. Here's a brief synopsis, coalesced, condensed my whole life into one PowerPoint slide. But one thing I really specifically wanted to show was, let me get the pointer options here. Okay, here we go. Is this right specifically here? When I first, born and raised in right outside of Pittsburgh, my dad was a steel mill industry engineer. My grandfather was a steel mill industry engineer. And I really envisioned that I would follow that career path. So it was really, as you can see, I highlighted and bolded the time at Johns Hopkins. That was really a life-changing, a career-changing event for me. I always envisioned myself following in the family tradition and really applying proven engineering concepts, cutting engineering concepts to industry challenges. And then really my time at Hopkins changed, and I really decided at that point in time, I really wanted to be pushing the envelope of engineering concepts to societal problems. And I really credit my time at Johns Hopkins for really changing my career life direction. And then after that, I went to Idaho National Lab, finished my PhD in computational fluid dynamics, kinetics modeling. And then really since that point in time, both at NRAL and at Colorado State University, have really been focused on clean energy. So that's really what I'm going to talk to you about today. So I really wanted to cover the drivers for change, some interesting technology advancements, really how we can tie that to human desire, desire to always improve our human situation. And I think really clean energy provides a lot of opportunities in that space. And then finally, probably most importantly, the exciting window of opportunity that exists for a change, both in the United States and around the world, to a more sustainable, better energy future. So I'll start with issues that we're probably already aware of. Climate change is obviously continuously on the news. I started one of my very first projects, postdoc projects, was actually doing climate change modeling for Los Alamos in the 1990s. And it was interesting at that point in time, we really didn't have the sophisticated models enough to really specifically predict individual impacts. But what we did predict is weather would become more volatile and more extreme. And it's kind of gratifying all these years later to say we were actually pretty accurate on that. So I think we're really seeing the implications of that. More extreme weather events. As we all know, you can't tie a specific weather event to climate change. But what you can do is more extreme conditions, and we're clearly seeing the negative global impacts of that. So there really is an imperative to do something about climate change. This one is kind of a more recent problem, if you will, but in a lot of ways, every bit as big of a problem. Single-use plastics are becoming the bane of society. Um, the recycle rate is quite low. They're disposed of very casually. They end up in oceans, plastic tides, um, degrading pristine beach environments, ocean environments, mountain environments, you name it. So really plastics are becoming, single-use plastics are becoming a very societal problem, both in the United States and globally. And it's really imperative of science and engineering to do something about that. And then finally, and in a lot of ways, most importantly, conventional internal combustion cars have major detrimental impacts on air quality. It's affecting the health of our population. Probably most importantly, it's affecting the health of our children. Air pollution, urban air pollution is a significant issue. It's a global health issue. And there's a lot of contributors to air pollution, but vehicles, conventional vehicles, are a significant contributor to that. So that's really kind of the situation that we are in. Society as a whole has really benefited from the extensive use of fossil fuels for electricity generation and fuel generation, but our commodity-based, low-priced energy with almost exclusive reliance on fossil fuels is having many detrimental impacts on human health, planet health, and it's really at the imperative of engineers and scientists to address that. So now I'm going to kind of switch gears. That was all kind of, I don't want to say doom and gloom, but that was really kind of highlighting the detriments of our current approach. So I really wanted to switch gears and focus on some positive developments. So I'm sure everybody in the call has heard about the promise. A lot of people are probably working in this field. The promise of low-cost batteries, high-capacity batteries, and how that can really enable a transition to battery-powered vehicles, battery electric vehicles. Interestingly enough, a metric was set up probably in the year early 2000s that once we achieved a battery cost of $100 per kilowatt hour, scientific wisdom, commercialization wisdom, is that would be when battery electric vehicles were truly competitive with internal combustion cars, gasoline powered cars, and they would have significant penetration of the marketplace to a point of taking predominantly being the majority of new vehicle sales. So you can see this chart in the middle really plots that, and you can see the dramatic reductions in 2010 to 2018. The reason this chart stops at 2018 is that it was when the data stopped being reported publicly. Now individual companies like Tesla, General Motors, BMW, a lot of vehicle manufacturers now consider that a proprietary technology. So it's not peer-reviewed published about what battery costs are, but a lot of true experts in the field feel that we've already crossed, especially for industry leaders like Tesla, General Motors, already have crossed that $100 a kilowatt hour threshold for battery cost. And then as you can see from this chart, that's when it's really expected that electric vehicles will really start taking off into the marketplace. So that's encouraging. I did get some data from, there's a lot of organizations out there that predict the future. As we all know, nobody has the ability to predict the future. It's impossible. But what you can do is look at trends, do various different assumptions. This chart here, in a lot of ways, to me, proves the obvious that since this is put out by the Energy Information Agency, a part of Department of Energy, so it's somewhat politically influenced in the fact that they take very conservative assumptions. And one of the this shows the conservative nature of their assumptions. What they predict, what this slide projects is vehicle sales as a function of the range of the electric vehicle. So what they're showing is if the electric vehicles only have a 100-mile range, essentially sales are negligent. And then once you get to 200, 300 mile range vehicles, sales dramatically increase. Interestingly, it doesn't show much of a market for plug-in hybrids. A lot of people would argue, probably correctly, that this is overly conservative, or the vehicles commercially available are already over 200-mile ranges. Some are more than 300-mile range. So realistically, this chart would probably be more meaningful if it took it up to 400 or 500. But what you can see is that seems to be the driver for consumer acceptance. So once we get these higher range vehicles, you'll really see a dramatic increase in electric percent. This is all light duty vehicles, cars, light duty trucks. So that would really be the predominance of new vehicle sales. This is also very encouraging. This shows the history of electricity prices in the United States and in various different scenarios. These are all extremely encouraging. And the fact that you see by the predominance of low cost wind and solar that electricity prices are going down. Like I mentioned, I would take the specific numbers with a grain of salt, but I think the overall trends are extremely encouraging. You see electricity prices going down, plus you see low carbon sustainable percentages taking over the mix of the electricity. So that's just very encouraging. First time really in, I can't think when, maybe in the 1960s, but even before that, that the long-term projections are electricity prices decreasing and also switching to more sustainable, lower polluting, lower greenhouse gas emitting. So that's very exciting. This just shows it for biofuels. Again, biofuels have come down to the point that they are maybe not now with the low crude oil prices due to COVID-19 restrictions and driving, but prior to the COVID reduced use of transportation fuels, biofuels are arguably competitive. And this isn't first generation biofuels. This is the more sustainable cellulosic, lignocellulosic biofuels. So this is really encouraging that you have battery electric vehicles, you have, so finally, before I sum up, let me move this. The other thing, most people wouldn't really consider this a sustainable energy technology, but I'll explain later in the presentation why I consider it a sustainable energy technology. Autonomous vehicles were really that they could have a major impact on energy use and sustainability, and I'll explain later what I mean by that. And then finally, this is a very convoluted, visually unfriendly slide, and that was very much intentional on my part. So, don't try to read all the arrows, because the point of all this was showing you that current chemical products, chemical intermediates, is very much an empirical process where you line up new chemicals with existing chemicals, and then you really look at current state of the art by looking at exact chemical replacements and then how that goes into the industry. It was really much more empirical, much more historical, not a lot of engineering science. So significant improvements in engineering modeling, biological modeling. As we all know, Jennifer Doudna, Emmanuel Chaparro won a Nobel Prize for CRISPR-Cas9. And that's a biological technique to tie physical properties, phenotypes to genotypes. Same thing in the chemical engineering space, where you can use atomistic scale modeling all the way up to continuum scale modeling to really specifically tie chemical structures to physical properties for chemicals, combustion properties, emission properties for fuels. This just shows kind of a very streamlined way of doing that, to use density functioning theory, quantum mechanical type of approaches, all the way up through the various different scales till you get to chemical reactors or you get to industrial scales. So by doing this, you can really streamline the process for chemical design, fuel design. It's much more rational. And it's much, I think, on a very positive side for commercialization potential. These type of approaches can be turned around from new chemicals to products in a matter of years, where the traditional approach would take matters of decades. So all of those are really coming together simultaneously. And that's giving us a lot of promise. As we all know, humans fundamentally have a desire to improve our situation. And that's a good thing. You know, when we remodel a house, we tend to make it nicer. We buy new clothes. We tend to buy nicer clothes. It's just inherently part of the human nature. So I think as you see me go through this presentation, that's the point that I'm trying to make. I think human psychology, the human desire to improve our situation has to be a fundamental part of this, as well as improving human health through air pollution, global health through the air pollution, waste disposal, climate change. But if we can do those simultaneously with improving the human condition, I think we'll get a wide scale acceptance, and it would really be something that would drive government investment, commercial sector investment, and really has the opportunity to improve human situation in everybody. So this is kind of an interesting slide. I'm not intentionally trying to throw slant at a mid-90s Taurus, but what I am showing is that this is two examples of one that got it right and one that didn't get it right. So for the first example, the Ford Taurus, the 1996 Ford Taurus, I think this is an example of a product introduction that didn't get the human desire to improve right. I think most people, even in the mid-90s, would argue that a Ford Taurus was not perceived as an advancement, wasn't perceived as an improvement on the current vehicle situation. So there really wasn't a market imperative to purchase and drive a first generation biofuel vehicle. It was just perceived as more of the same. And then this is what I think Elon Musk deserves a lot of credit for. When when Tesla introduced the first generation Tesla Model S, which was the 2012, marketing the human desire to improve was a dramatically part of that. And people perceived electric vehicles as an improvement over current cars. It's a nice looking vehicle. It performs well. Interestingly enough, 8 years later, it ages well. So Elon Musk and Tesla got it right, and the biofuels community really didn't. And to even that carries over to this day, whereas biofuel vehicle sales are a small declining segment of vehicle sales, whereas electric vehicles are just dramatically increasing. So really what I'm going to walk you through now in a kind of a fast manner is how do we get there? So how do we use these technology advances to really transform our energy system to a more sustainable? So here's a slide that just shows how you have to look at energy, not in isolation. You don't look at industry, transportation, commercial buildings, industry in isolation. If you look at them as a complete connected system, which in reality they are, and then it's the infrastructure underneath that underpins all those, it really opens up opportunity space to think about this more holistically in a greener, more sustainable context. So what I guess my argument, NREL's argument, is we should really look at sustainability and low carbon energy as central to energy planning, that really should be what the future energy mix is based around, because that really is what provides us the opportunity to move energy, product space, chemical space to more sustainability. So how do you do that? So that's really what I'm going to walk through now. And I'm going to talk about three specific approaches for doing that: integrated energy pathways, electrons to molecules, and then finally circular economy. So let's talk about integrated pathways. So today's grids were built arguably 100 years ago. They were mostly built around large coal-based plants, then nuclear plants, oil plants, but large fossil-based plants. hundreds of megawatts, if not gigawatts, that control the frequency on the grid. And that's really how the AC grid generation system in this country is developed. As we go forward, especially if we incorporate a significant portion of renewable energy, and one thing I will say is there's a lot of comments made that renewable energy, due to its intermittent nature, obviously solar only generates electricity when the sun is shining and when the sun is shining, and wind only does it when the wind is blowing, and so those are intermittent, and that's a significant issue in today's grid, and that absolutely is true. But we're never going to get the sun to shine 24 hours a day or the wind to blow 24 hours a day. So we really have to accommodate for the intermittent nature. And these smart grid approaches, by looking at two-way power, by looking at ways you can store power without having large battery installments, all these really opens up a lot of ways to overcome the intermittent nature of renewable energy and really not have to supplant that with complete fossil backup and others. So smart grids are really microgrids. Some people will refer to these as microgrids, but they're really two different terminologies for saying the grids of the future. One thing I did want to touch upon, electric vehicles. Electric vehicles are exciting in a lot of ways, but one way that people might not historically think of is the life expectancy of electric vehicle. Inductance motors, if you I've seen a number of papers on this, if you extrapolate the life of them to electric vehicles, you can easily come up with a scenario that electric vehicles last 1 million miles or longer, where internal combustion cars, just 250, 300,000 miles are really the top end of their life expectancy. So if you really look at electric vehicles, if you only look at electric vehicles as a one-for-one replacement, and personally, that's what POV stands for, personally owned vehicle, you're really missing some of the true potential of these electric vehicles. So if in fact we have vehicles that are capable of lasting, and this, the fundamental assumption, I must clarify that one of the fundamental assumptions on this is we get battery technology to last that 1 million miles. But the technology, that's not a pipe dream. The technology development of battery technologies is clearly positively trending in that direction. Current batteries probably no, but hopefully the batteries of 5 to 10 years in the future are capable of that. So here's an interesting example looking at ride sharing. So a typical personal owned vehicle is driven at 12K miles per year. That's a 5% utilization factor. So if these vehicles are going to be fleet owned, Uber, Lyft, or whoever, and they're going to be fleet vehicles that are out there, they're going to be most likely a 50% utilization factor or even above, which means as a minimum 120K miles per year. So that really opens up the opportunity for electric vehicles. And then if you look at electric plus autonomous, you can bring the cost per mile traveled to less than a personally owned vehicle. So now Uber and Lyft would not be competing just with taxi cab companies. They would be competing with people buying personally owned vehicles. And that really opens up ride sharing opportunities, using ride services, ride sharing for commuting, less traffic jams, less cars on the highway infrastructure. So that's really kind of exciting, and really the opportunity space that, and then obviously if these are all electric vehicles, the improvements in urban air quality would be dramatic, less traffic jams. And then additionally, since they're fleet vehicles, I've heard about the intermittent nature of solar. Something is referred to the duck curve. That means that the peak solar generation is from 10 to 2, but the peak use is when people go home. This is non-COVID, and use electricity from about 5 o'clock to 8 o'clock. So these fleet vehicles could be plugged into the grid. They could provide the storage capacity, get lower cost of electricity by doing that, and really alleviate the utilities having to buy their own batteries for storage. So really significant out of the box opportunities with electric vehicles. Light duty. Mid duty and heavy duty are harder to electrify. So here's where advantaged biofuels come in. Looking by using carbon oxygen bonds, you can reduce soot emissions. You can improve cetane. You can really look at some lower temperature combustion, gasoline compression ignition, lower temperature compression ignition. And really, biofuels can open up some space here in these vehicles that are harder to electrify. I mean, eventually in the long term, these vehicles might be electrified, but the pathway to accomplishing that is much longer term than light duty. Trucks, heavy duty trucks, highway trucks, maybe advanced biofuels, or maybe even hydrogen fuel cells, or maybe even electric charging on the interstates, wireless charging on the interstates. All sorts of opportunities looking at all the various different transportation modes. Jets and marine, maybe sometime in the midterm to long term, planes, short haul planes could be electrified, but probably anytime in the near term, there's a need for jet fuel. Biofuels have a lot of potential here, low carbon jet fuels, advanced jet fuels, same thing with marine. Hard to envision ocean transport vessels being electrified. So biofuels could really have a nice potential to reduce the carbon footprint and environmental footprint. So that really shows what we could do with integrated pathways. A lot of opportunity space. Are these technologies completely economically competitive with existing technologies? In most cases not. Some cases they are, like the battery electric vehicles and light duty are. But a lot of improvements in battery technology, smart grids, a lot of research to be done in storage integration. But really the upside is huge, that we can have sustainable societies, sustainable cities, lower greenhouse gas, lower urban congestion, lower emissions, higher air quality, better air quality. So really significant upsides. Let me switch now to the industry space. As we know, process industries are almost exclusively based on fossil feedstocks, large economies of scale. Electricity has historically been a low cost, high cost input. So most existing fuels and chemical plants are 24/7 operation, extensive, very large scale. And if you offered them low wind and solar intermittent electricity, it's just not something their process can accommodate. So if you switch to a process like this, where you're using electrochemical reduction of CO2, water splitting, and then you're using the latest in biocatalysis, electrocatalysis, there's industrial situations where you can show you make polymers, materials, chemicals, and fuels where your only inputs are CO2 and water and renewable electricity. So boy, the opportunity space to transform process industry to sustainable energy, sustainable place is huge. The last bullet that I showed is, I mean, it's very fair to say that these are currently not economically competitive with current fossil fuel approaches. But with R&D, it's really the first time in human history that we've had low carbon, no carbon electricity. If you were using traditional coal-based electricity or even natural gas, you're actually generating more CO2 than you're sequestering. So there's no point to it. But now you could actually be sequestering carbon in industrial products. The other advantage of this, which is really exciting, is in the developed world, kind of similar to cell phones, where in the developing world, never really had the infrastructure, the telephone infrastructure, the electric infrastructure that the developed world had. But as far as communications, they leapfrogged all that by going to cell phones, really didn't need to run telephone lines. Same type of thing. With a lot of the developing world doesn't have electric power distribution, doesn't have extensive transportation networks. But by doing these small distributed conversion plants, where your really only inputs are solar cells, CO2, and water, you could actually even look at distilling CO2 out of the atmosphere. You could really look at leapfrogging these developing countries into industrial space, economic revitalization, better human condition without the need for all that infrastructure. So that's really exciting, both in the developing world and the developed world. This just shows like I mentioned, this is, especially in the developed world, this is not cost competitive, not even close, maybe a few high niche, high value niche market products. But really to get this down to cost competitiveness, significant R&D, technology development, engineering development is required. Biocatalysis, electrocatalysis, hybrid processes, a lot of advanced engineering, carbon capture reduction, CO2 reduction, really some exciting opportunities both in the chemical engineering space, mechanical engineering space, electrical engineering space, to really transform industry to this more sustainable model. And like I said, the opportunities in the developing world where they could actually leapfrog into these type of industrial processes without the infrastructure is very exciting. Finally, let me finish with challenges with plastic to recycle. The number one problem with plastic to recycle, I could have just written this bullet, is as simple as that. It's not economic. Current processes are not economic. Virgin plastics are cheaper and better. And until we solve that, I mean, we can put bans on single-use plastics, and we can look at, which I think we should, less water bottle use and all that kind of stuff. I think it's good. But the reality is, until we figure out, why are, when you drive across the countryside, why don't you see rusted cars sitting all over the place? Well, because it's economically attractive to recycle cars. Why don't you see wood waste or tires sitting all over the place? Same thing, because it's economically attractive to recycle them. And that's really, I think, what could transform this huge problem. If we would come up with the technologies that we could get recycled plastics, at least to the place where metal recycle or wood recycle, where it's at least as good, if not in metal's case, actually better. If we could get that to that place, then this whole huge problem would go away. And that is a huge problem, huge challenge. But luckily, we have a lot of good work. We have a lot of good people that are already looking at it. And apologize for for your non-chemists, chemical engineers in the audience. I apologize for the organic chemistry on this slide. But the point of this slide is not to go through the individual molecular structures. What it is to show you is that if you intelligently incorporate biomass is carbon, oxygen, and carbon, hydrogen, and oxygen, where hydrocarbons are just carbon and hydrogen, obviously. And by understanding that chemistry and taking advantage of that, and the inherent carbon-oxygen bonds can be weaker, can provide cleavage sites, both chemically as well as biologically. You can open up an opportunity space in plastics where you make plastics inherently biodegradable, or even better, you can upcycle plastics, whereas you can take, like in this particular case, a polyethylene terephthalate monomer, and you can actually use biomass amine-based chemistry, and you can actually upgrade it to a Kevlar material, in this particular case, something that has almost 100x the value. I mean, I don't want to over exaggerate and say that these are commercial technologies. Obviously, these are chemical transformations in the lab and have a long way to go to commercial viability. But I think the opportunity space that this opens up of understanding the chemistry, understanding the introduction of biomass, oxygen in a chemically rigorous manner, you can really open up the space that plastics are inherently biodegradable, or even better, are economically attractive to recycle. And if that can be done, that could really have significant impacts on the plastic challenges in this country and the world. Like I said, it's not, the big challenge is poor economics. Plastic recycle is just not economic for a multitude of reasons. That would be a whole presentation in and of itself to explain all those reasons. So I glossed over them here. But the challenge is really how to do that, how to get the chemistry, how to get the engineering processes to really be able to do that. And then just shows the research to be able to do this. But this opportunity space is very good. I think creatively, collectively as a society with the engineering expertise, the chemical expertise, the infrastructure expertise, we have the ability to do this. So this is really a focus of humanity that we should really be focusing on. So with that, I'll end and just say thank you. What I tried to impress upon the audience as a whole is I think we have a lot of technologies that we can really cleverly deploy and develop, that we can really use sustainable energy, not only to improving human health and environmental health, to really improving the quality of life. And if we can do that, I think this space is just going to really take off and have huge benefits. So with that, I'll stop and thank the audience and open it to questions.
Thank you for that wonderful presentation. And now it is time for our question and answer portion. You can ask, audience members, you can ask your question by push the Q&A button and type your question. And we already have two, and they're related, and that has to do with the hydrogen economy. And you mentioned briefly hydrogen. How does hydrogen fit into the future state of our energy? And just broadly, how will it, what parts of our energy sector will that impact?
That's a good question. That's a really good question. I think 5-10 years ago, probably the way I would answer that question, or most experts how would answer that question, is in the transport segment and talked about light duty, mid duty, heavy duty, probably not aeronautic, but probably would have talked about land-based heavy duty, light duty. I think that really the way the technology is developing and the scale of it and the investments being made, most vehicle manufacturers, light duty manufacturers, has switched over to battery electric vehicles, really feeling that is better value proposition, more near term, and the upside is every bit as good, if not better. But so now most of that's focused on mid duty and heavy duty, and there's still a lot of research being done, a lot of investments being made. Water splitting still is not economically as attractive for producing hydrogen with renewable energy as steam methane reforming, which obviously, unfortunately, comes with a high CO2 footprint. So water splitting, renewable, low carbon hydrogen is still a challenge. Granted, some onboard reforming technologies can have some impacts there. But I think that's a big challenge. If we can develop water splitting technologies with renewable to get hydrogen costs down to, now they're competing with renewable electrons and batteries from wind and solar, that there's a lot of opportunity space in the hydrogen economy in that regard. But that's really the big challenge right now.
All right, next question. What is the role of politics and policy in ushering in the transition to sustainable energy in a timeline that's fast enough to halt the worst effects of climate change?
Good question. Good question. If you would ask me that question earlier in my career, I would have probably told you that policy and government mandates should drive the change. As I've gone through my career, I've rethought about that. I've rethought that position. And now I'm more of a supporter of free market economies and natural market pull situations. And the reason I've changed that is because politics in this country, if not the world, especially the United States, as we all know, are very volatile. And they tend to have very dramatic shifts from one party to another. So the problem is government mandates are not sustainable over the long term. So unless we get a more stable political framework to work on. But I confess I might have expertise in a lot of areas, but stable political framework is not one of them. So I'm not really sure how you would enact that. So I think that natural market pull, natural market forces, and natural human psychology to show that sustainable energy, renewable energy is better for society. and then supported by the appropriate government policies to incentivize that is the right way to go versus specific mandates. Because I just worry about the political stability of those mandates over the long term.
So we have a question about microgrids. Microgrids coupled with solar and renewable generation seem to be useful in the developing world for tasks on the order of cell phone charging. But how do you see sustainable industrial development progressing in that area?
It's a good question again. Really good questions. I would envision solar cells that you would design. Like for instance, I was part of this project funded by the Gates Society. Very, very interesting. And what we were doing was producing amino acids that we were folding into complete protein powder for human consumption in sub-Saharan Africa, because malnutrition, specifically lack of protein, is a significant concern in those areas of the country. And we were those areas of the world. And we were powering that by solar cells. So we were able to make enough protein to feed thousands of people in underprivileged, impoverished villages. So I think there's, was it economically competitive with protein powder that you could get in the developed world? No, it wasn't. But, the problem was in those parts of the world, there just isn't a transportation infrastructure. There isn't a refrigeration infrastructure to support that. So manufacturing it locally and consuming it locally with minimal infrastructure is really game changing for improving the human quality of life in those type of places. So I think in the developed world, we always worry about economic competitiveness. In those parts of the world, economic competitiveness is less of a concern. It's really improving the human condition. So it's really looking at specific products, food products, light products for reading, specific products for improving the education levels, the health of those individuals, the products that they need with minimal infrastructure. And having an isolated microgrid that doesn't require, in the United States or Europe or any developed part of the world, microgrids are supported by the macrogrid. That's still what provides frequency control and stuff. And that part of the world, that's not possible. So really to look at very enabling microgrids for those type of products to improve human quality, like the example I gave you with the protein for human consumption. I think the opportunity space to really have dramatic improvements on the quality of life is quite dramatic with these type of solar powered or wind powered type of applications.
So a question I had, and now it's echoed by an attendee, I was going to be asking you a little bit about storage, because the wind doesn't always blow, the sun doesn't always shine. And so it's my understanding storage is an important issue, but in particular, one of our attendees asked, where do you see the role of the subsurface for various energy storage systems, for example, hydrogen in subsurface caverns and reservoirs, and how it could tie in with intermittent renewable energy sources?
Another good question. Pumped hydro storage, salt cavern storage of hydrogen, air bladder storage, geological storage, all those have significant potential and will be needed, just for your point that wind and solar is inherently, it's an intermittent power source. So right now, that one chart that I showed that showed the generation costs coming down, but the wind and solar are cheaper, are the lowest cost, and they're not even close to being mature technologies, where natural gas, combined cycle, and coal are arguably mature technologies. So the potential for reduction is dramatic. So that divide will only increase. However, it's somewhat unfortunately tempered by the distribution and storage costs. So for instance, there was a situation in Maryland, Virginia, I don't think it was last year or 2 years ago, where the polar vortex came down in January and the sun didn't shine for almost a week, and it was record cold, where that all it dramatically changed the renewable penetration, because the only thing that saved that part of the country, well, which where Johns Hopkins is in, was the antiquated coal plants that were able to be brought online. So the true potential can't be realized until we get these, and developing just battery-based, lithium-ion battery-based storage is just not cost effective. And unfortunately, if we did do that, then we would compete against the batteries for electric vehicles and drive up battery costs. So issues with fleet ownership, some of the stuff I was talking about, fleet ownership of electric vehicles where they're plugged into the grid and they provide two ways, the geological storage, all those issues have to be brought to bear. In some cases, that backup electricity is only used once a year, twice a year. So the economics of that type of storage is a bit of a challenge. So there's still more research, there's still more technology development required in that regard.
So you mentioned the lithium batteries. I have a question here about batteries. And that is, how do you address the environmental impacts of battery disposal versus the impacts of fossil-based fuels? Is the point of inflection achieved through differences in volume or battery recycling processes?
Battery recycling processes. I didn't actually cover that. That's an interesting area of technology development. So I saw some chart. Matter of fact, I'm sure you could probably just Google it and find a chart. But the percentage of lithium-ion batteries that have been recycled as a function of time. So the x-axis is time and the y-axis is percentage. So up until very recently, unfortunately, very small percentage of lithium-ion batteries in our cell phones, computers, watches, you name it, were being recycled. So now Apple, Samsung, even Tesla, General Motors is kind of ahead of that, Nissan, have really taken great strides in developing their vehicle infrastructure, their battery infrastructure for ease of recycle. Same challenge with the plastic recycling is it wasn't economic. I don't think it's still economic, but a lot of places like California, Colorado, I'm not sure where Maryland stands, but some leaning states are providing incentives to really provide the technology development necessary to make it recyclable. Car batteries are already economically recyclable purely because for car batteries, for high discharge voltages, you require cobalt. So just because of the higher value of cobalt, that though they're already economically attractive to recycle, but the cell phone batteries and the computer batteries are still on the cusp. But fortunately, that's trending in the right direction.
So we got another question about the environmental impact of batteries, and that is, can you comment on the fabrication of the infrastructure, such as the manufacture of the batteries with associated hazardous waste and necessary generation of energy to fabricate these batteries, mining of the minerals and so forth?
Yeah, good question. That's an issue. I mean, that very much is an issue. As we know, I mean, fracking and horizontal drilling has dramatically increased the geological portions of the world, North America specifically, where oil is now economically attractive to recover. That wasn't true in the 70s and 80s. So even though there was arguably enough crude oil, it was geopolitically concentrated in the Middle East, which was causing some geopolitical tensions and issues, obviously. So a lot of people have studied that specific issue with lithium-ion batteries. You know, are we going to just cause the next geopolitical concentration? And that was true. Early generation lithium ions with cobalt, and for whatever reason, the metals, the name of the metal's not coming to my head right now. They actually made a movie about it, Kurt Beckinsale, with the Democratic Republic of Congo. And then all the child labor and all the human rights abuses that were taking place there, horrible situation for the mining of this particular metal. So, I don't have a magic answer for that because, any technology since humankind has come out of caves has never been a panacea. There's always been pros and cons. And I don't want to give you the illusion that battery electric vehicles are 100% perfect. There's always going to be cons. But what I will say is policymakers, scientists are doing a better job of understanding those situations. So for the car batteries, we're already developing nickel-based batteries that will give the same current discharge intensity of cobalt, because cobalt's an current acceleration technology enabler, where we can do those same functions with nickel. It's not as effective now, but I think we can get there. And the huge upside is it solves those geopolitical challenges with the DRC and those type of issues. So there's no magic solution for that. Those are all very valid concerns, but really the best way is to research them, address them, and use good engineering scientific practices to come up with workarounds.
Well, thank you. Thank you, Tom, and thank you everyone for your questions. It's now time to conclude today's program. Another thank you to our speaker, Tom. You are truly a leader in your field, and I appreciate your taking the time to join us today. And again, thank you, Gordon and the Croft family. Thank you to Linda and the Billig family, and a special thanks to all of you for attending today's lecture. Have a good evening.
Thank you.